All right. So last class we talked about acid strength, really the definition of acids and bases, where just to reiterate, the acids have hydrogen and they want to get rid of hydrogen to make it H plus or H3O plus, the hydronium ion. And the bases, they are producing OH in solution. They may have or may not have OH, but they produce it in the solution. And we ended last class talking about the acid strength. And if you have 100% ionization in water, you have a strong acid, meaning a strong electrolyte. And usually, which we're going to learn about how the strength of the acid bond, of the H bond to the rest of the molecule applies. Wait a minute. Wait, you guys can still hear me, right? Okay, you should be able. Yeah?
Yes.
Okay.
No, you should have left him hanging.
Because I heard like when Windows is done with something, it makes that noise, or when Windows like has an error, it's like like it has a weird noise. I heard that, so I'm like, wait a minute, something happened, but no, nothing happened. But nice job. Who said you should leave me hanging, Rebecca?
No.
Oh, okay, sure. No extra credit for you. Everyone else gets extra credit for being honest.
Hate it here.
Yeah. Okay, so we have the strong electrolytes, meaning with strong acids and strong bases. They're complete ionization, 100% ionization. Okay, and then we talked about the strong acids. So how do we identify the strong acids? And I gave my little mnemonic for the strong acids, and that's Hickel, HCl, Hibber, HBr, high, Hickel, Hibber, high, Hino, which is HNO3, Hiclo, where there's actually two Hiclos, HClO3 and HClO4, and then Hiso, H2SO4, sulfuric acid. So these are the main strong acids that you guys should know, which is so Hickel, Hibber, high, Hino, Hiclo, both Hiclos, and Hiso. So that's the best way to memorize it. And yeah, I can say it fast. Hickel, Hibber, high, Hino, Hiclo, Hiso. Like I can say it fast. I invented it. So Hickel, Hibber, high, Hino, Hiclo, Hiso. So if you memorize it fast, boom, good. If you know how to write it down, you can say it, but not spray it, and then be able to write it down. That's good. And then for weak acids, if you know this, you know the strong and the weak, because the weak acids are the ones that simply do not fall in this category. So anything that is not Hickel, Hibber, high, Hino, Hiclo, Hiso is considered a weak acid, which means that it is a weak electrolyte and that it has a very low percentage of ionization. That means the percentage, and let's say for HCl, we have a high percentage of ionization. That's actually 100%, or very close to it. We have the HCl breaks into H and Cl minus, or if we want to talk more Bronsted-Lowry, we can say that HCl plus H2O yields H3O plus Cl minus, and that's actually what happens in the solution. And we can say that if we have 100 molecules of this, of HCl, 100, this is now 100 molecules of this and 100 atoms of Cl. It breaks apart completely. But for a weak acid, so anything not in this list, meaning something like HF, if you have 100 molecules, you might have only one ionization. So when we mean weak acid, it's a very weak acid in comparison to a strong acid. There aren't going to be many acids that are maybe 50%, 60%, like somewhere in the middle. It's either a lot of ionization or a very little amount of ionization. So that brings us to a weak acid. So here we go. So much less than 1% ionization in water. So very, very small amount. And we're actually going to use ice charts to figure out the pH of these weak acids and to see where their equilibrium lies, and we can see how much H3O concentration they have, meaning what is their percent ionization. So we'll be able to calculate this number that is much less than 1. So here's some examples of other weak acids. Hydrofluoric acid. Oh, there's a typo on the books part. They said hydrochloric acid. This is actually a bad typo. They should mean hydrofluoric acid, which is HF. Sulfurous acid, which is a diprotic, meaning it has 2 protons. And both forms of it, meaning the H2SO3 and then the HSO3 minus, both of those are considered to be weak acids. acetic acid, formic acid, carbonic acid, phosphoric acid. So basically anything that is not Hickel, Hibber, high, Hinoa, Closo. That's the basic rules. Any questions on that? No? Okay. So with acids and bases, just like we did for any reaction that forms equilibrium, we have what we call an equilibrium constant, or in acids and base terms, we call it an ionization constant. So that's this K. It's this ionization constant. And if you have a small ionization constant, and remember so this constant, big K, whatever, it's an equilibrium, ionization, there's a lot of different terms for it, but it means the same thing. It's the ratio of the product concentrations over the reactant concentrations. Oh, I like that mnemonic. So I brought no clean clothes. I guess that makes sense. Like HSO4, HI, HBr, HNO3, and an HCl and CL. Oh, yeah. Okay. Well, no, it's missing. You're missing a CLO. I like mine better. I'm being biased, but I like mine better. Anyway, good feedback. So this constant is calculated the same way. It's a ratio of the products over the reactants. Now, if you have a small ionization constant, meaning this ratio between products and reactants is going to be small, that means most of the reactant concentration, or most of the concentration in the equilibrium equation, is going to be towards your reactants. In an acid-base reaction, like HF yields H plus F minus, if it's more towards the reactants, that means it's a weak acid and the percent ionization is very low. So at equilibrium, most of it's going to be here, which means very weak acid. So the smaller the ionization constant, the weaker the acid. And sometimes you'll see ionization constants that are very small. They're 10 to the negative 10th, 10 to the negative 11th. You may see them very small like that. So, and that makes sense because when you have weak acids, they're going to have a very small ionization constant.
So that's what it meant when it said less than 1% ionized, right?
Exactly.
Is that like
exactly.
K is less than 1?
That means K is much less than 1. It's not going to be as in a percentage because, you have things, your concentrations that are 2 powers.
Right.
So, but it's going to be very small. Yeah. Okay. So something else that's important to know is if we have a strong acid or a weak acid, we need to know what the attraction is. We need to know how the strength of the H bonding to the, let's say, anion, how that correlates to acid strength. And it's an inverse proportionality. So if you have a weak bonding between acid or the H plus and the anion, then that's considered a strong acid because it's easier to come off. So an example of this is HCl. So we're going to compare our 2 hallmark strong and weak acids, so HCl and HF. The reason why HCl is a strong acid is because the bond between H and Cl is much weaker than the bond between H and F. So if you look at polarity, so H is a 2.1 of electronegativity and Cl is 3.5. Obviously, it's a largely polar molecule, but the polarity, it being polar, just means it can dissolve in water. But the polarity difference here is pretty weak in comparison to HF, which is 2.1 and 4.0. This is a lot stronger. So the fact that this bond, this polarity difference is a lot bigger means that it creates a stronger bond. To create meaning a higher partial charges, minus for the fluorine, positive for the hydrogen. If that's the case, then then this is going to not want to break apart. The H is going to be strongly bound to the fluorine, and it's going to create a strong attraction, which means a partial ionization. So that's important to keep in mind, is that the strong acids, you have a weak attraction in the H to the rest of the molecule. The weak acids, you have a strong attraction between the H and the rest of the molecule. And then you have this acid ionization constant known as Ka. So for bases, you're going to have Kb, which works exactly the same. And again, this is exactly the same to regular K, to Kc, to Kp. All the different equilibrium constants that we learned, they're very similar to this. So it's calculated the exact same way. So remember, we have this funny looking F thing. We can just say that this is the equilibrium equation like that. And we have your acid mixed with water. The acid will give up its hydrogen. Remember, it will donate. It will be a proton donor. It will donate its hydrogen to the water, which will then become H3O plus. And then you'll have your anion, your acid anion, which is A minus. And then because you have this equation, which has water as a pure liquid, because remember, you are basically adding the acid to the water. Water as a pure liquid will not be considered in the ionization constant, just like liquids and solids aren't. So your total ionization constant will be Ka equals the concentration of H3O times the concentration of A minus over the concentration of the initial acid. So if you have a larger Ka, that means you have a strong acid, because most of your molecules are going to be on the product side, meaning they're going to be H3O plus and the A minus, which means there's going to be a large ionization percentage. So maybe 100%. So calculating ionization constant, exactly the same as doing the equilibrium constant. And we'll be using this as in examples. All right. So you have, here's some examples of some weak acids and their corresponding ionization reaction and their Ka and their pKa. So pKa is literally the negative log of Ka. So if you think about this, if you have a small Ka, right? So the expression, sorry, I dropped my pen. The expression, the products over reactants, is low. That means it's going to be a weak acid. So Ka is low, weak acid. So phenol on the bottom right here, very weak acid. We don't even consider it to be an acid at all. Very weak. Its pKa, meaning the negative log of the Ka, will be relatively large, which means it's going to be a very, very weak acid, or even basic. So we consider phenol to be kind of almost basic. That's how weak of an acid it is. So what we're trying to say here is that if you increase the Ka all the way up to, let's say, chlorous acid, which is a legitimate weak acid, then the pKa decreases. And for what kind of scale? There's another scale I'm not mentioning here. That's the most common scale for acids, which you guys should probably know, that low numbers mean more acidic. And which one is that? And Christina, good one. Phenol so basic because he is weak. He never hits the gym. Haha, good one. Okay, so what's another scale that I'm forgetting here? It starts with a P. pH. Good, Ahmad. Good, awesome. So pH. pH is another scale that the lower the number means the more acidic. So lower than 7 is acidic. And this is true for pK as well. Not lower than 7, but lower numbers generally mean more acidic. And you can even have pKa that's negative. And you can have pH that's negative. Or sorry, you can't have pKa that's negative. Well, yeah, you can. Yeah, you can. You could have pH that's negative as well. So just keep that association in mind. Okay, so let's take a look at a question. So consider the 3 generic weak acids, acid A, B, and C. The images shown here represent the ionization of each acid at room temperature. Which acid has the largest Ka? So remember, Ka is products over reactants. So the larger the products, meaning the larger the Ka, the stronger the acid. So which one of these is going to be the strongest acid, meaning it has the most ionization? B. Yes, Rebecca, good job. B, because look, how many ionized particles? 1, 2, 3, 4. This one has 1. This one has 2. So the answer is B. Good. Okay, so which acid is stronger based on the Ka? HF, good. So A. So still some discrepancy here. So if you have a small, so Ka, remember, it's HA, meaning the acid plus the hydrogen plus water equals H3O plus the acid. So the expression is going to be H3O plus times A minus over HA. If the top is higher, meaning the whole expression's higher, that means the acid is going to be stronger. Right. So it's Ka, not pKa. If pKa, then it's the opposite. And keep in mind, pKa's are usually in whole numbers, like 1, 2, 3, things like that. So they're not usually in 10 to the negative numbers like that. Okay. Any other questions on that? Okay. Sorry, I got a missed call. All right. So then we have autoionization. So what this means is that we can consider this. To figure out the pH or the acid-base balance in a solution, both of really every aqueous solution that's water-based, get it based, has a combination of H3O plus and OH minus. That balance of H3O plus to OH minus is what makes the aqueous solution acidic or basic. If it's more towards the H3O plus, it's more acidic. If it's more towards the OH minus, it's more basic. That's all it is. And what you put in there, what the solute is, all it does is it takes the H's from the solution, or it gives the solution more H's in order to throw off that balance. So that's all an acid-based solution is. It's just a fight over H3O plus and OH minus of the water. So in a normal normal DI water, meaning deionized, no ions in it at all, pure water, the concentration of H3O plus is the same as the concentration of OH minus, and they both equal 10 to the negative 7th molar. That's true. That's just a fact. They both equal 10 to the negative 7 molar. And if you multiply them together, so the concentrations together, 10 to the negative 7 times 10 to the negative 7, you get 10 to the negative 14, which is a constant, which is a global constant for ionization, which we have right here. So we have our Kw. So we have this number. It's always the same number, this Kw. So the ion product of water has a symbol called Kw. And it's the concentration of H3O plus times the concentration of OH minus in any solution that's aqueous. If you have a really acidic solution, the H3O plus is going to be very high, and the OH minus is going to be very low. If you have a basic solution, it'll be the other way. But no matter what, if you multiply both of them together, you'll get 10 to the negative 14. So does that concept make sense? Now, a good follow-up would be, why is that important? Because when you're calculating the concentration of H3O plus, or OH minus, or if you're calculating pH, or if you have pH and you're being asked to calculate for the POH, which we'll learn about soon. You can use this equation. The concentration of H3O plus times the concentration of OH minus equals Kw. You can use this information to help you find the other one. And you know what Kw is. It's 10 to the negative 14. So this can be helpful. And remember, it's not going to be on the first exam, of course, right? Because first exam is just chapter 15 and 16. But this information will be on the second exam. So and I would say memorize it. It's just easy to do. Because if you can go right from any aqueous solution. And yes, Luke, all of 16. It's only 15 and all of 16. All the way up through Le Chatelier's principle. Okay. And here we go again. So as H3O plus increases, the OH minus must decrease so the product stays the same. And they're inversely proportional. And that makes sense because if you have an acidic solution, this would be the H3O plus would be higher. If you have a basic solution, the OH minus would be higher. Any questions there? No? All right. Okay, so yeah, we talked about this already. All right, so which one is acidic? So remember, the balance is the base or the neutral environment is 10 to the negative 7 times 10 to the negative 7, where they're equal, equals 10 to the negative 14. So in which case is it acidic? Not C. Oh, yeah, acidic. A, yes. Nice save. But maybe I did say basic on accident. I don't know, but acidic. Okay, good job. So the reason why, there's two reasons why. One, if you look at the definition of what neutral is. So neutral is where you have the H3O plus and the OH minus, both at 10 to the negative 7 molar. If it's higher than 10 to the negative 7 molar, like A is 10 to the negative 3 molar. That's a lot higher. That means it's going to be more towards the acid. And then the OH concentration will have to be 10 to the negative 11. Very, very low.
So if it said OH is equal to, it would then be C, correct?
Correct. If it said which one's the most acidic, and it said OH is 10 to the negative 9, for acidic, OH has to be small. So the smallest one would then be the most acidic. But in this case, we're using H3O plus, which is the signature for acidity. And then we didn't even talk about pH yet. You can just calculate the pH of this solution. So all you have to do is calculate the pH. pH equals negative log of 1 times 10 to the negative 3. And this equals 3. The pH for this one is 3. pH for this one is 7. pH for this one is 9. So based on that, obviously A is the most acidic. Low pH means acidic. And then here we go with that. So the correct way, or the most efficient way of calculating acidity or basicity is the pH. And it is derived from the Kw, what we just learned, that in any aqueous solution, H3O plus times OH minus is going to be 10 to the negative 14. And of course, pH that's less than 7 is acidic, pH that's greater than 7 is basic, and equal to 7 is neutral. And then, yeah, I mean, you just calculate you put it in the calculator and calculate it, and it's negative log. And pH can be negative. It can be greater than 14 as well. So even though traditionally we say the scale is from 0 to 14, in some cases where, look, you could have a concentration of hydrochloric acid that's 20 molar, and that's going to be a negative pH. Or you could have a concentration that's so low or you have a concentration that's so high of, let's say, sodium hydroxide, that it can be a pH above 14. So all that is possible. So here's some gastric juices. Here's some pHs. So gastric juices in your stomach, you have pH 1 to 3, so it's very acidic. That's why if you throw up, it burns because you have all that gastric juices coming up. Limes are pretty acidic. Lemons, soda, beer is acidic. Rainwater is pretty acidic, a little bit acidic. Like acid rain is like 3 to 4. Human blood, 7.4. So we're all basic. Sorry to break it to you. White eggs or egg whites, not white eggs, egg whites. To 8, milk of magnesia, household ammonia, and 4% sodium hydroxide is 14. You could have 10% sodium hydroxide, and that's like 16, 17. So that could increase. Okay. All right. So what does the pH number imply? So each pH number, because it's based on a log, means a factor of 10. So if you have a pH 1 versus pH 2, that doesn't mean, oh, the pH 1 has like one molar more hydrogen than the other. That's not true. It means it has 10 times the amount. Because if you want to go back to their concentrations, remember how we got to pH in the first place. Something with a pH 7 is 10 to the negative 7 molar. That equals 7, meaning of the H3O+. For something that is 10 to the negative 4 molar, that's 10 to the third higher. That's 1,000-fold higher. The pH is going to be 4. Or if we just do 10 to the negative 6, it's going to be a factor of 10. The pH is going to be 6 now. So a pH unit of 1. Oh, milk of magnesia is like a, yeah, it's like a laxative. It's like a stomach. It's like an antacid kind of thing, but it's like stronger. Yeah. Kind of, I mean, yeah, all right. Yeah. All right. So that's pH. Now, in terms of sig figs for pH, we usually do traditionally pHs to do 2 decimal places regardless. So we really don't follow the rules of sig figs that much. So just keep that in mind. It's always 2. Okay. Then we have POH. Now, this brings me to a funny joke. One of my friends still my best friend, he was my freshman year roommate. When we taking Chem 2, we were studying together about pH, POH, and he came up with the genius idea. He's like, why isn't there a PO? Like, is there a PO? I'm like, oh no, that's not how it works. That's not it, dude. But that's what I think about when I think of POH. But there's no PO. It directly corresponds to the 2 parts of a solution that determine basicity or acidity, meaning pH, meaning the hydrogen concentration, or the hydroxide concentration, which corresponds to the basic part of the solution. So then we can figure out the POH the same exact way we figured out pH, which is the negative log of the OH concentration. In a very basic solution, the POH would be very low. So it's the actual opposite of pH. So in this case, POH is less than 7, it's basic. POH is greater than 7, it's acidic. POH is 7 means neutral. And at all the times, they're kind of inverses of each other, meaning the pH plus the POH equals 14. So this means if you have something that's very acidic and the pH is 3, the POH is 11. You have to add them up and they equal 14. But if you look at POH being greater than 7, it's acidic. This means if you want to take it to the equation level, that the concentration of OH in this solution would end up being 10 to the negative 11, which is very small. Since OH is very small in concentration, that means the H plus would have to be or the H3O plus would have to be very large, and thus you have an acid. And here's exactly how the scales compare to each other. They're basically the opposites. They are the opposites. Okay, any questions on that? So the reason why this is important is because you can use OH to find the pH of a solution. You could find the hydrogen ion concentration of a solution, and you could really do a lot with it. So we're going to do examples in a minute. But okay, so pK. So you have pKa and pKb. Now, instead of blindly memorizing this stuff, I would suggest walking through the logic. And the logic is all of these numbers derive from Ka or Kb, which is the equilibrium expression. If Ka is large, so we'll walk through this. We'll walk through this bullet point. So if Ka is small, right? If Ka is small, that means, well, I'll write it down just so you're not confused. So you have H3O plus A minus over HA. If Ka, and this is equal to Ka, if Ka is small, that means everything's more towards here. That means it's a weak acid because at equilibrium, most of the molecules are going to be on the acid phase, on the reactant side. If that's the case, then the pKa would be large because if you take the negative log of this, it'll then be a larger number. This number would be small. Therefore, the negative log of it would be large. This number might be 10 to the negative 9th. The pKa would be 9. So if the Ka is smaller, the pKa is larger. So that means the weaker the acid, meaning the stronger the base. So if you have it's good to be making these associations. If this is the case and you have a weak acid, that means you have a stronger base than a strong acid is, of course. So if you have the stronger the base, the smaller or here we don't say it right, but the weaker the acid, the larger the pKa. And oppositely, the stronger the acid, meaning the more towards the products on the top, the larger the Ka and the smaller the pKa, which is right here, because pKa is negative log of Ka. Does that concept make sense or is that confusing? Feel free to input. I think it may take some time to just rationalize it. Good? Okay. And then for bases, you have the stronger the base. If you have a stronger base, that means the base is going to be more towards the products in the Kb expression. So Kb expression would be the OH minus times the base plus, the basic part, the basic cation. And then you'll have BOH. It'll be like that. And if it's a stronger base, that means it's more towards the product. The Kb is going to be big, but that means the pKb would be small. Okay, does that make sense? A little bit? All right, let's do some questions. Oh, question? No? Okay. All right, so we're going to calculate. I don't know why the top is always blue. Well, we'll do parts. Well, okay, we'll do. Oh, I guess I'll walk you through these. There's some, next slide, there's some more we can do together or on our own. So calculate OH concentration of each of the following and determine if it's acidic, basic, or neutral. So if you're given the H3O plus concentration and you're being asked to calculate OH concentration, what you could do is use our definition that the H in every aqueous solution, H3O plus OH minus is 10 to the negative 14. You can plug in 7 times 10 to the negative fifth into here and solve for OH minus, and you get 1.3 times 10 to the negative 10. And then what you can do, you can see, all right, what is larger? That's the easiest way to do it. Or you can do the negative log of the hydrogen of the H3O plus concentration. That would give you a pH value, and you can determine from the pH value, is it acidic or basic? Or you can see which one of these concentrations is larger. Is it the H3O plus or is it the OH minus? And clearly it's the H3O plus. Wherever you have an H3O plus concentration larger than 1 times 10 to the negative 7, it is acidic. That's an important thing. If you have H3O plus concentration larger than 10 to the negative 7, it's acidic. If you have an OH minus concentration that's larger than 10 to the negative 7, then it is acidic as well, or then it's basic. So it's just getting used to all these terms, really, getting used to how they relate to each other. Any questions on that? Okay, now for B, we can clearly look at here, calculate OH concentration. We would do 10 to the negative 14 divided by this number, and you get 6.7 times 10 to the negative 6. And we can see that it's basic because the H3O plus concentration is a lot lower than 10 to the negative 7. So that means it's basic. And then for this one, it's neutral because it's 10 to the negative 7, and it would be neutral. Okay, so now on your own, well, I'll bring this down. For these ones, let's do C. So let's do C by yourself. I'll give you a minute, and then I want to hear the H3O plus concentration from someone and determine if it's acidic, basic, or neutral. Anybody get it yet? And Sumi, yes, I will try to upload my PowerPoint with the annotations. Anybody got the answer for C? pH is 4.9. That looks right to me. And it is acidic, right? So it's acidic because the OH minus concentration is lower than 10 to the negative 7. It's a lot lower. It's 10 to the negative 10. That's acidic. And the way to figure out the corresponding H3O plus concentration is you do 10 to the negative 14 divided by 8.2 times 10 to the negative 10. And you do some stuff, and then you get whatever the concentration is, which if the pH is 4.9, it would be 10 to the negative 4.9 molar. You probably don't get that in your calculator, but whatever. That's the same number that it equals. Okay. Yeah, same thing. 1.2, 10 to the negative fifth. Thank you, Rebecca. I'll write that down. 1.2, 2, 10 to the negative fifth. Okay. Any questions? Nope. Okay, moving on. Conceptual question. So as the pH of a solution increases, what happens to the acidity of the solution? B, good, decreases. pH goes up, that means more OH, more basic, less H plus, less acidic. All right, now let's get into some fun stuff. How do we determine the pH of a weak acid? because we don't know exactly what it is. Oh, it's, yeah, less than 1% ionization, whatever. We can actually figure it out based on what we know about ice charts. So let's just cut into it. Let's just do ice charts. All right. So we'll do one together, and then we'll do one by ourselves. All right. So find the H3O plus concentration of 0.1 molar of HCN, where we have our Ka is given to us. All right. So keep something in mind before we start. Remember, we talked about approximating X, where I said something about this, the K value. If K is below a certain point, we could approximate X, because that means you're going to have such a low amount of turnover from reactants to products that it's going to be a negligible number. Can anyone tell me what I said, or how does that apply to this question? You have no idea. Wow. Okay. I see you guys were listening. All right. I will just tell you that then. I did say, and it was in the notes for chapter 16, that if you have an equilibrium constant that is less than 10 to the negative fifth, and you have a relatively high concentration, which 0.1 molar, you can consider that not high, but your Ka is 10 to the negative 10. So it's extremely low. That means your turnover from reactants to products is going to be so low that when you have the minus K part of the ice chart, it's going to be negligible. And when we're doing the quadratic, that K or that X will be negligible and cancel out. So that is what we can do when we get to that point. So let's do this one together. So you have HCN plus water as a liquid. Remember, it doesn't count towards the equilibrium. Is both ways, goes to H3O plus CN minus. Now we have initially, so we'll write our ice chart, ICE. Initially, we have 0.1 molar. We have none of that, doesn't count. H3O, we have 0. CN, we have 0. So change. Since this is balanced, we have the change. It's minus X. We can cancel out this whole row. Doesn't count. H3O plus X. This is going to be plus X. Then we're going to have 0.1 minus X, X, and X. And then we have our Ka expression, which is simply H3O plus at equilibrium times Cn minus at equilibrium. So X squared divided by 0.1 minus X. This is going to equal our Ka value of 4.9 times 10 to the negative 10. So now, can someone tell me what we're going to do with this equation based on what I said before?
You said X is negligible, right?
Right.
So can we just put it at 1 and just take it at face value or cancel it?
Meaning, okay, so you're right, but the X I said that I meant was negligible was this minus X part, not the X squared. That's still, you still need to solve for something.
Oh, because we're subtracting that.
Right, because you're subtracting a super small number from 0.1. So this is negligible. So that makes sense. If you have a small Ka and a really large initial value, initial concentration, that means you're basically taking $1 away from Bill Gates. It's going to be negligible. So we can make it nothing. So the equation you're solving for is X squared divided by 0.1 equals the Ka. And exactly, you're right, Christina. Good job. And Rebecca. Okay, so then you multiply that, boom, boom, you get X, and what is X going to be? According to this, X is going to be 7 times 10 to the negative 6th. So now we know how to get this far based on our ice charts. 7 times 10 to the negative 6th. But now the only difference is that we have acids and bases, and we can put this number into context. of acids and bases and pH. So this number X corresponds to the H3O plus concentration. Ding, ding, ding. Very important. We need that to calculate everything we need to know. We can calculate from that number, doing this ice chart, we can calculate H3O concentration, OH minus concentration, pH, and pOH, and pKa. Well, we could do that from Ka, but from that, we could also do pKb if we wanted to. So we can do everything. Now, it's saying find the H3O plus concentration. We have that. Furthermore, let's just find the pH. So it would be, well, it would be negative log of 7 times 10 to the negative 6th. Does anybody want to solve that for me? .15. Nice, nice. That makes sense. I always look at context. Does that make sense? Very important. HCN. Is it an acid? Yes. It's a weak acid because it's not in Hickel, Hibber, High, and Noah, Cloiso. So we expect it to be in the weak acid, and there's not a lot of it either. There's 0.1 molar. So we're expecting 4, maybe not even 4, maybe like 5 or 6 range. That's what a weak acid is in terms of pH. That's exactly what we get. We get 5.15. If we got the answer as 1, that means there's something wrong, because usually pHs of 1 are either if there's a large concentration or it's a strong acid. So always be smart with your calculations. Are there any questions on this one? No? Okay. So what we're going to, here's a solution written out. What we're going to do is you guys are going to find this one on your own. So find the H3O plus concentration and find the pH. So, and pH. And you know what? Find the pOH as well. And then I'll give you 5 minutes until 8:22. We'll go over it together, but I need help from you guys to do the calculation since I'm lazy. And yeah, go do that. All right, let's get started. So I guess I'll start writing. All right, hydrofluoric acid. So HF plus H2O yields H3O plus F minus. We have our ice chart. So what is our initial for HF? Oh, you got answers already. Okay, I was going to go stepwise. Thank you. All right, we have eager beavers up in here. Who uses that terminology? I don't know. Eager McBeaver, is that a thing? Whatever. So H2O, we don't have anything. It's liquid. H3O plus is 0. F minus is 0. Change of HF, what is that going to be? Eager McBeaver. That's a thing. X, good. Eager McBeaver is a thing. I've heard it before. I'm pretty sure I don't
think it is.
All right.
Okay.
I'm pretty sure my mom or dad have said it, or some adult in my life has said it before. So it must be a thing.
It's a boomer thing.
Probably. Anyway, H3O plus, what is it? Great job.
Plus X.
Good, plus X. Great participation. What about F minus? Plus X, good. Now our expression, HF. Good, 0.25 minus X, H3O plus. X and X, good. So now our expression would be X squared over 0.25 minus X equals 6.6 times 10 to the negative 4th. Now for this one, can we approximate and get rid of the minus x? No. It's borderline, but if it's ever borderline, the answer is no. So we always want to come up with the best answer or the most precise answer. So we can solve the quadratic, and what do we get for x? Well, let's see. Let's compare. It's a good exercise. So for those of you, someone who didn't approximate, what did you solve for x? What did you get? Anybody?
X equals 0.0125.
0.0125?
Or negative 0.0131. Or
well, it's not the negative one. It's the positive.
Yeah.
Yeah. So
0.0125.
Okay, good. All right. So now, Christina, what did you get for your approximated value? Or anyone else that approximated? $0.0128. Okay, good. So that's close enough, but you could see how it's still borderline. If it was 10 to negative, if the Ka was 10 to negative fifth, 10 to negative sixth, then it would be very, very close. But this is still borderline. Honestly, you want to know my opinion? If you have a borderline question on the exam and it would take you too long to solve it, approximate. So it's just quicker if it's on the borderline. But ones that are yeah, exactly. Yeah. So that's what I'm saying, Luke, is that the 0.0128 is the one where you approximate. 0.0125 is when you don't approximate. So they're very close to each other. So technically you could approximate even though it is on the borderline, but the more correct thing would be to not approximate. But either way, if you're crunched for time, you can approximate. That's what I would do. It's a good test taking strategy. If you know a quick way to get to an answer, even if it's not perfectly right, if it's still kind of close and you save time, do that. But I'm here to teach you the correct way to do things, even though it may not be the best way to do things for taking exams sometimes. It's all about strategy. All right. So then from this, we know the H3O concentration is X, right? Because it's right here. But what about the pH? What did we get for pH? Oh, yeah, without approximating. So what you can do is you can cross multiply. So if you cross multiply, meaning multiply this over there. So here's what we'll do. And we'll just do it over here. So let's take this equation, pretend it's over here, but we'll do x squared equals 6.6 times 10 to the negative 4 times 0.25 minus x. Then you can subtract and move this whole expression over. And you have x squared minus 6.6 times 10 to the negative 4th, 0.25 minus x. You factor these in. You factor the 6.6 10 to the negative 4 in. You get a quadratic expression that equals 0. Then you have A, B, and C. And then you use the quadratic formula. Wait, why is my thing messing up? There we go. Oh no, my PowerPoint just closed. There we go. Okay. Then you use the quadratic formula where it's, what is it? 2a over the square root of 4ab minus 2c. Something like that. And type it in math way. I mean, I use Wolfram Alpha. Yeah, but you basically make it a quadratic and make it all equal to 0. And then you can solve it using the quadratic formula. Oh, sorry, I forgot. This is, I flipped this. So it's negative b plus or minus square root of b squared minus 4ac over 2a. I botched that wrong. That's why I haven't used it in a long time. I'm a chemistry person. But yeah, there's the quadratic formula. So, and of course, this is the plus or minus. You'll get two answers. It's always the positive answer. And at one point in the homework for one of the questions, there was two positive answers. And one of them clearly made more sense than the other. That's a very difficult case. You're not going to get that on an exam. But just to know in your future endeavors, if that does happen, you always have to look at it logically. I think that one of the questions was you got two positives, but one of the positives was larger than the initial concentration. So you can't remove more than that was there. So logically, it would make sense. The other X wouldn't work. But anyway, that's how you do that. Okay, any questions on that? Okay, we're almost done. Let's do this one. And then we'll talk about percent ionization. And then
we didn't do the OH.
Oh, sorry. So we have the pH. pH is what, 5? What did we get? 5.15 or something?
I got the pH is like 1.9.
1.9?
For a hydrofluoric acid.
Let me see. Oh, we have different pHs now. So Christina got 12.1. Rebecca got 11.1.
Yeah, well, I mixed that up because
so
I got 10 to the negative 3 instead of 10 to the negative 2. So I got the same one that Christina got.
So that's 10 point. That doesn't make sense. Well, I guess, wait. Yeah, it doesn't make sense. It should be higher. It should be lower than that. So the negative log of 0.0125. 0.0125. Yeah, 1.9. So pH equals 1.90.
Yeah, that.
Yeah, that. Okay. Okay, good. Right. And that makes sense. It's an acid. It looks like a pretty strong acid, but it is a weak acid. And the reason why the pH is in the strong acid territory is because look at the concentration. For the previous example, we had 0.1 molar and the Ka was much lower. In this case, the Ka is much higher, meaning it's a lot stronger than HCN, and the concentration is more than double. So it makes sense that the pH is going to be a lot lower and to be more acidic than the example we had before. And to be more specific, you can tell the difference. So like the Ka here is 10 to negative 10. The Ka here is 10 to negative 4. That's a factor of 10 to the 6th. And you can estimate that, yeah, you can say that the pH here being 5 and the pH here being 1 or 2-ish, maybe around 5 or 6 off. And when you factor in the concentration, it's a bit different, but it makes sense logically. Okay, good, Christina. So what Christina said is correct. And then the POH would be 14 minus the 1.9, which would be 12.1. Sorry, I had to sneeze. Okay, I'm good. All right. So, and you can see that with using the approximation, you're off by a little bit, but it's in this case, even though it's borderline, you can still use the approximation. It won't give you that far off. It'll give you less than a % difference. So don't worry about that. And then, Christina, you have another comment. Also, F is right near BR and I and CL. You're getting to a point that we're talking about that more next week. But basically, if you have the halogen acids, right? So HF, HCl, all the way down, the strength of the acid increases going down. And the reason why is because, like we said before, the electronegativity or the polarity of the molecule is larger with HF in comparison to HCl. So HF, the the strength of HF is going to be a lot stronger, meaning the ionization is going to be harder to achieve than HCl. Then HBr, it's a lot easier to achieve. Then HI, it's even easier to achieve. So the bond between H and I is a lot weaker than the bond between H and F. And we learned about this a lot last semester when we talked about bond length, the atomic radius, meaning the larger the atomic radius, the weaker the bond strength. And also we talked about polarity a little bit and how the bond strength differs by charges. Stronger charges plus or minus mean a stronger bond, and weaker bonds, weaker pluses or minuses equal weaker bonds. So, and a longer bond length. So it all has correlation. It all makes sense. Okay. So POH, yeah, 12.1, exactly. All right. So what we're going to do is, we'll do one more example. We'll do this one. Okay, so I'll give you guys 5 minutes to do this one. We'll go over it, then talk for 10 seconds about percent ionization, because you should, based on what we just learned, you should know how to figure that out. It's just doing the total. It's just doing the H3O plus divided by the HA at equilibrium. And then after that, we'll be done. So I'll give you until 8:40 to do this one, because there is some discrepancies. I feel like you do need another example. And then after that, we'll almost be done. So, all right, go do that one. All right. Let's fill in they already have the ice chart for us, so that's nice. All right, so given, here we go. What does it say? A 0.1 molar weak acid, so we don't know what it is, has a pH of 4.25. Find Ka. So the pH immediately can tell us the H3O plus concentration. So that's the first thing you do. Then you plug that into the ice table for the equilibrium for H3O plus. So for HA, we have an initial value of 0.1 molar. Put that in there. What's the change? Minus X. Good. Changes for the products. Plus X. Good. And plus X. Nice. Then the total equilibrium 0.1 minus X. And then you have, oh, look at that. X, we already have the value for it. So X equals 5.6 times 10 to the negative fifth. And you have X there. So for the finding Ka, well, you would basically just do, or can anyone tell me what you have for the expression?
That was my question, were you going to do 5.6 times 10 to the negative fifth squared because there's two of them in the products, or no?
Yes,
okay.
Because the products, you know what X is equal to already. And without the, let's say this was just X, this would be the expression, X squared over 0.1 minus X. Same thing we've always been dealing with. But now we know that X is 5.6 times 10 to the negative fifth. So we can just plug in this value for minus X, or for 0.1 minus X, and for X. Exactly. Christina is correct with what she wrote in the chat. And then you can solve that. And what do you get for Ka?
(3.14) times 10 to the negative 8.
That's 10 to the negative 8. All right. Almost pi. 3.14. So that's good. Cool. So this is acidic, right? Weak acid, because you have 4.25. Yeah. And then from there, you can solve for other things, but yeah. Okay. Cool. And how would you find Kb? So you know that well, I don't have to worry about that. No, I don't have to worry about Kb. You know how to solve for OH minus, right? You just take 10 to the negative 14 divided by your H3O plus concentration. And then you can find your POH from that. So yeah, that's about it. Any other questions on that one? So same concepts. Okay, so then just to wrap up, These are just some, we'll just talk about for 2 brief seconds, percent ionization. Now, you can figure out the percent ionization. And it's another way to measure how strong an acid is. And we already figured out, we know how to do pKa. We know how to do Ka. So, right, Ka, if the Ka is larger, that means it is stronger. If it's lower, that means it's weaker. The pKa is the opposite. It's kind of like pH. pKa and pH work the same, meaning if it's lower, it's more acidic. If it's higher, it's more basic. For percent ionization, you could imagine, the lower the percent ionization, the weaker the acid, meaning most of it is not going to be ionized. It's going to stay in the reactant. And you can figure out percent ionization from doing the ice charts. It's simply the concentration of the ionized acid, meaning H3O plus, divided by your initial concentration of the acid, which is your HA initial. So it's going to be your H3O plus at equilibrium divided by your initial H plus, HA plus, times 100. And usually for the weak acids, it's going to be very small. But you would think, so here's something that we'll leave with, and we'll probably go over it next class as well, but I'll leave you with this, that you would think that if you increase your concentration of a weak acid, that the percent ionization will be about the same, right? Because you're just adding more molecules. This is not necessarily true. If you increase the concentration of your acid, the percent ionization will act, if it's a weak acid, well, really any acid, will actually decrease. But we're talking mainly about weak acids because strong acids are 100% all the time. It will, if you increase your initial concentration, the percent ionization will actually decrease. And the reason why is because if it's 1 per 10,000 molecules that are ionized, you add another 10,000 molecules, you might have another one if that, because your solution is going to be more heavily biased towards your reactants. And it's kind of like the concept of like seeding, meaning what that means is like if you have a ton of reactants and it's very stable to be in the reactant state, it's going to, the higher the concentration of that reactant, the more stable the solution is going to be overall. And there really isn't going to be any molecules that turn over to product. So the more concentration of the acid you have, the lower the percent ionization for a weak acid. If you have a little bit, so increasing, so if you, so if you, by the opposite, if you have a little bit of acid, then you're going to have maybe out of 100 molecules, you might have 1. And that 1% is a lot larger than 10 to the negative 8%. So it's kind of like an equilibrium thing. It has to do with energy too. It's just, this is another thing that to understand, that you may be given a question on like exam 2. If you have 0.1 molar of hydrofluoric acid and 0.2 molar, which one will have the highest percent ionization? And the answer is the one with the lowest concentration. So, and you can figure that out by the ice table also, because each you'll have the Ka for that. But yeah, okay. So I'll leave you with that.